what acceleration is. And hopefully you've learned that acceleration is equal to dv over dt. I think they teach that in calculus classes. That's its definition. It's the derivative of velocity, the derivative of time. So it's finding out the acceleration at that moment in time. And that's equal to minus kv. So that wasn't too bad. And now we have to do the integral. And this is where it starts to get a little bit more tricky. To do an integral, if we did an integral right now, we'd be integrating on velocity here and time, and we can't integrate two different things on in the same integral at the same time. So what we have to do is get all the v things together and all the t things together. So what we're going to do is bring dt over to this side and bring v over to this side. And since m is a constant, we'll just put it over with k here. So a little algebra, I'm going to divide by that, so that's going to make that minus k over m, dividing the m to the other side. I'm going to bring this v over here, so that's going to come to the bottom, so that becomes dv over v. And then I'm going to multiply both sides by dt, so that's going to bring that out here to solve that. Okay, and now we're pretty much set to do our integral. Well, that's going to look like this, and that's, I'm going to write it like this. That's 1 over v dv is equal to the integral of minus k over m dt. We're doing this for velocity, so we want to do this over the interval from the initial velocity to the final velocity, or any velocity we care about in the future, and the initial time to the final time, there, like that. Okay. Okay, so the problem here is that if we want to do the integral on this, v dv, we can rewrite that as v to the minus 1. 1 over v is v to the minus 1. dv, that's v over v. The problem is that the rule that we've learned is that you add 1 and divide by the new exponent. Well, that's not good, because that's v to the 0, which is just 1. But then, minus 1 plus 1, that's 0. We got a 0 in the bottom, and math people don't like that. So we can't use that rule. But there's an integral that you can look up. And the integral is that x over dx is equal to the natural log ln of x. So that's good, because that applies here. Basically, what we have is v to the minus 1, and that is dv over v. And that's in the form of this. So what's the integral of this? It's the ln of x. So this becomes ln, the natural log of, well, it's not x, it's v, natural log of v. And we're evaluating that still, we haven't done this, over this interval. And on this side, let's not forget this, we have the integral of tot minus k over m dt. So on this side, we're integrating with respect to time. But I don't see any time in here. Where's time? Well, there really is a time in here, and it's t to the 0, because it's 1. So let's do the integral rule, t to the 1, so it's 0 plus 1 over 0 plus 1. Well, that's easy. That's t to the 1 over 1, so that's just t to the 1, or t. So that integral is easy. But what about the k and the m? K is a constant, m is a constant. They're not changing. This car has a fixed mass, and it's got all this constant stuff, which we're kind of ignoring, but it's just stuff that's not changing in the problem. I'm actually going to bring that outside of the integral, because I don't need to deal with it. So I have this, and what's the integral of dt? Well, we just did it. It's t. That's t0 to t. So that ends up becoming minus k over m, and the integral times t. You can put that up top. And then I still have to evaluate that from t0 to t. How do you do this? Well, this is final minus initial. So That's the interval. It's the change that occurs. So final minus initial would be ln of v, final, minus ln of VO. Final minus initial is the change from here to here. And then on this side, same thing. It's minus kt over m minus the initial, so that's minus kt0 over m. And that would be plus. Minus and minus would be plus, but we don't have to deal with that because what time did it start at? Let's say that this block started at time 0, as most physics problems do, and so that drops out. We don't have to deal with that. Now, there's a thing in math that is like ln of x minus ln of y is equal to ln of x over y. That's just a math thing. I don't know what they call it, but it's something that you should know. So we can use that here so that we can make that into ln of v over vo is equal to minus kt over m. Now, we're just going to stop for a minute and sort of ask ourselves what the heck we're doing here, because it's been a while. We've been doing a lot of math steps. Remember, back here, our goal was to find a formula that tells us how fast this thing's going at any moment in time. Even though the acceleration is changing, we want to find a formula for velocity. And we did a lot of work here to get here, and we're starting to get close. Because look, there it is right there. But we've got to get it out of there because right now it's in this, trapped within this natural log. Well, let's say you had x squared in a derivation and you were solving for x squared. How would you, let's say x squared equals 10 or something. How would you solve that? Well, you would take the square root of both sides, because the square root is the opposite of squaring. What's the opposite of lnning? What's the opposite of natural logging? It's the opposite of a natural log. It is e to the. So if you do e to the ln of x, that's like taking the square root of something that's squared. So that would just be equal to x. So we're going to do is a little trick here. We're going to go e, this is all separate crap here, e to the ln of v over vo. And whatever we do to one side, we have to do to the other, just like this is still regular algebra applies. Kt over m. So we raise both of these to the e, and because this is the undoing of that, it's like the square root of the square, that just leaves us with v over vo. So that just becomes this. And we're almost done. Let's just bring this vo out here to the side so that this becomes vo e to the minus kt over m. And that's our formula for how fast this block is going under laminar flow at any moment in time, t, with these constants k and m. All right, let's stop there for a second. Okay, so to sort of make a little bit more sense of all this, I graphed it. And I just put it into here. I made up some numbers. For VO, I had 10, and then I made up a number for K. I said I had a constant of 4 and a mass of 12. And so let's take a look at what's happening. The car has an initial velocity. What's its initial velocity? It's 10. This is a graph of velocity versus time. So here it is. At 10 meters per second, and that's how fast it's going. And at that moment, there is a lot of air pushing on it because it's going fast. So what happens because the air is pushing on it? Well, it starts to slow down. But the force is not constant. Now, if the force was constant, if this was a graph of a force of friction slowing us down, it would just be a straight line because the force would be constant, so the acceleration would be constant, so the velocity would constantly decrease. But because most of the force is occurring early on when it's going fast, therefore it's going to have a greater amount of change, therefore acceleration early. So this line is steep, but later